this is a major topic for the course. Okay, we are going to be doing proofs in various forms throughout the course. Okay, and this is your opportunity to understand what proofs are. Okay, so what are proofs? Well, it's a way of establishing that a proposition is true, right? So how do we? Oops. Okay, so how do we establish that given some proposition P, how do we establish that it's a true statement? Okay. Well, the problem comes out because the kinds of statements we are interested in are statements about infinitely many things. So we might have a statement like this, but we might also have some statement which says for all x, y, z belong to the positive integers, something, right? For all n greater than or equal to 3, for all x, y, z belonging to z plus, x to the n plus y to the n is not equal to z to the n. And so now what you have to do is you have to establish something that holds. So here you could establish this is true just by saying, well, I know this is true because, look, here's what works. X equal to 3, y equal to 4, z equal to 5. Right? 3 squared plus 4 squared equal to 5 squared. So it's true. There exists x, y, z such that x squared plus y squared equal to z squared. Now here, you want to show something holds for every natural number, every n greater than or equal to 3, for every x, y, and z. Okay? How do you show this? Well, to which you can maybe ask, why do I care? So I claim that if you're a computer scientist, you care about infinite objects. It comes with the profession. You write a program. So you've written a program, P. Takes as input x. Okay. And what you want to do, what you want to say is that you've written this program, it's a complicated program, it's computing some function, okay, some interesting function. It's supposed to compute some function f of x. Okay. You figured this out, you're very proud of it. You wrote the program. Now you want to know, is this program correct? What does it mean that it's correct? Well, it means for all x, p of x equal to f of x. Right? There's a whole area called program verification. And theorem proving. Right? It's in programming languages. Okay. There's also circuit verification. You've created a circuit. It's supposed to, perform to certain specifications. How do you know it's really doing what you think it is? You could test it on certain inputs, but how would you be sure if it's a really important, if it's a really important program, really important circuit? How do you verify that it really does what it's supposed to? Okay, so now proofs are about taking these infinite objects and saying statements about infinitely many things and saying, here's why we know that they are true. Okay? And it's a different standard of proof. You know, it's a different standard of truth. When you do science, you say, well, Newton's law of gravity, you know, we verified it. In some sense, we proved it. You know, it's something we accept, right? But how do you actually verify it? By doing experiments. So you say, well, let me try it in many cases, and then I'll believe it's true, always. Right? That's how you do science. Here, it's a different thing we are trying to do. We are trying to say, how would we actually be convinced? How would we actually establish beyond a doubt that it is true for infinitely many cases, all of them? Right? That's what this enterprise is about. Okay, so now what's the form that these propositions are going to take? Well, usually they take the form for every x, p of x implies q of x. That's a very general form of the statement. Yeah? So, for example, okay. So let me back up a little bit and let me say, we are going to do in this lecture. What I'm going to do is many examples of proofs, so you can see what proofs look like. Many of you will have seen these proofs before. Hopefully, you have in high school. Okay? They're about numbers. Okay? But we are going to look at them from a slightly more sophisticated viewpoint. So to try to illustrate to you what's really going on behind proofs. So you understand what's the concept. You know, why is it important? Okay? And then, as we go along in the course, we are going to be building up. You know, we are going to be studying many things, and as we study them, we are going to have to prove things about them. This will help you understand what we are doing there. Right? So it's showing you what, hopefully you know, even if you don't, these are some of the most beautiful proofs from mathematics. They are simple proofs. Some of them were known to the ancient Greeks, and we'll talk about them, and you'll see how pretty they are, how clever they are. All right, so these are about all these proofs are about numbers. So let's say about the integers, and mostly about division. When does one number divide another? Okay? So remember, we say that A divides B. We write it as A with a bar and B. That's notation. If and only if there exists some integer D such that AB is equal to A times D. Right? That's what it means to divide. We also say, we may also say, use notation A does not divide. Right? We just put a little stroke through the vertical bar. So now, we might say, well, for all A, B, C belonging to Z, if A divides B and A divides C, then A divides B minus C. So what do we want to do? We want to do, we have some proposition P and some proposition Q. And we want to say P implies Q. this proposition is a function of ABC, so P of ABC, Q of ABC. Right? We want to say P implies Q. All right, so now what are we going to do? Well, we are starting at P. We want to get to Q. What we want to do is take baby steps from P to Q. And we want to say, well, actually, it's completely clear when you look at it that P implies P1. Some other proposition. You know, you take a step forward. You say, actually, this also implies P2. Well, what we're saying is P and P1 both imply P2. You know, from everything we know on the left, we can also get P2. And then this also implies P3. And so on. This implies Pn. And in fact, Pn is equal to Q. Okay? So if this implies this, this implies this, this implies this, we chain it forward, and we get to Q, then we say, look, we can collapse the chain, and now P implies Q. Okay? So what are we using here? We are using this fact, which you should really verify for yourself, that if you have three propositions, P implies Q and Q implies R, then P directly implies R. Actually, how would you do that? How would you know whether this is true or not? Does that look... Just think about it for a moment. So, is this something that looks like something you should be able to do, or does this throw you for a loop already? Can you say in sort of a couple of words what we would do here? A truth table. Yeah, you could do a truth table. Okay. Should we do a truth table? Let's do it. P, Q, R, P implies Q and Q implies R. P implies R. Okay. So let's see. What are we trying to do? We are trying to say these two are the same. Right? We want to say, another way of saying it is, in all cases, this entry is the same as this entry. So now we fill out all the entries of the truth table, and we say we check to see that this entry equal to this entry. So let's fill out a couple of entries. I won't do all of them. Any one that you'd like to see? So what should I fill in here? True. True. False. Another one? Well, let's follow this through, and then you can tell me the next one. Okay. So P implies Q. Is it true? Q implies R. Is it true? False. So this is true. This is false. What about the AND? What about P implies R? False. Okay. Let's do one more case. Anything? I'm sorry? True, false, true. Okay. P implies Q. False. Q implies R. True. What about this? This is false, true, so this is? What about the other one? Oh, sorry. This one's true. So they are not identical. I didn't say it correctly, did I? Sorry. You know, it was my mistake. I misspoke. So what did I do wrong here? Sorry. When I translated this, I translated this incorrectly. What I was saying was P implies Q and Q implies R. Then P implies R. They're not identical. What I'm saying is this implies this. right? Sorry, let me say this again since I made a mistake. Let's say this again. So what the claim is here, sorry, we are translating this into English. So what is this saying? What this is saying is this is the same as P implies Q and Q implies R. This whole thing implies P implies R. Okay? Right? It's not the same thing. It's that when you have these two conditions, this is automatically true. Right? When this is true, this is true. When this is false, it can be anything. Right? Okay, that's what you're getting. Actually, when this is false, this can be anything. Okay? Okay. So I won't go through the table again because, you know, if you find another problem, we'll have to stick here and change it again. So okay, I'm kidding, right? It's okay. All right. Okay, so sorry, let's go back to this. Okay, so what we are doing in this kind of proof is we are saying we start from P, we want to get to Q, we are going to find these simple statements in the middle that, you know, these simple steps that show us how to get from here to there. Right? It's finding a path. Okay, so let's do it. Okay, so what are we given? We are given A divides B and A divides C. Okay. So what does this mean? By definition, it means that there's D1, A equal to B times D1, A equal to, C equal to A divides B. B equal to A times D1, right? So A divides B, B is equal to A times D1, C equal to A times D2. By definition of divide, okay. And then B minus C equal to A times D1 minus D2. Therefore, A divides B minus C. Okay. So this was definition, simplification, definition, and we're done. Okay. Let's do another one. Let's do a slightly simpler one just to illustrate it a little better. All x, okay, x is odd when x squared is odd. By the way, you'll notice that sometimes I'm being a bit sloppy. I'm not saying belonging to Z. I should really be saying that, right? I should really be telling you what I mean by this. You know, I should be, when I say for all x, there should really be a universe here. Okay? Sometimes I'll be sloppy and I'll say I'll leave it out because in this context it's clear we are talking about the integers today, right? So just for convenience I'll leave it off, but then you are understanding in your mind that that's what I'm actually thinking. Okay. So again, what we want to do is start with P, get to Q. So x is odd. Another way of saying this is x equal to 2a plus 1. We want to say x squared is odd. That's like saying x squared equal to 2b plus 1. Right? That's just definition of odd. But now we want to get from one to the other. So how do you do this? Well, we do a set of implications. X is 2a plus 1 means x squared equal to 2a plus 1 whole squared. X squared equal to 4a squared plus 4a plus 1. And now, putting in b equal to 2 times 2a squared plus 2a. No, b equal to just that. We have x squared equal to 2b plus 1. Therefore, it's odd. Right? So we filled in our implications. We started from here. We wanted to go here. And then we filled in its baby steps. That's our proof. This is called a direct proof. If this is all there was to proofs, it would be very boring. Okay, but these are the simplest kinds of proofs that there are. Okay? There wouldn't be a whole subject around it if this is all there was. Okay? It turns out there are cases where you want to get from P to Q, and you can't find a path. And then what are you going to do? Okay, and that's where we get into something more interesting. That's where proofs start getting more interesting. And that's where something new comes into this picture. So let's see what that looks like. Okay, so let's do another example. By the way, sorry, let's step back here. You know, we had to remember, I started by saying we are proving something about infinitely many objects. You know, so this is a statement about all integers. It's infinitely large. This is a finite proof. It had only a few steps. But where were we handling infinity here? I mean, I just said x is odd, you know, x squared is odd, but where did we deal with infinitely many cases? Of course, x was arbitrary, right? We didn't say what x was. It's any integer. We proved it for any integer here. That's how we handle infinitely many cases. Okay. All right. So now let's say we are proving this following statement for all dn. If d divides n, then and d is odd, sorry, n is odd, then d is odd. Okay. Yeah, d divides n is odd, that's p, then d is odd, that's q. So we want to do the same thing again. We start with p. We want to go, you know, we want to find p1, p2, etc. So eventually we get to q. Okay. So we start. We write down, well, n is odd. We want to conclude d is odd. So let's do the same thing. Well, n is odd. N equal to 2 times a plus 1. We want to conclude d equal to 2 times b plus 1. Now, how do we fill it in? So n is 2a plus 1. Okay, it's 2a plus 1. But what do we know about its factors? How does it factorize? What are its pieces? Who knows? I mean, how do you know? It's just a number. It's an odd number. Now, what do we, we can't get started. It's sort of hard to get started. So now you look at this and you say, well, this is what I wanted. I wanted a path down here, but I don't see any path. I mean, this seems like empty space for all I can tell. So how would I prove that P implies Q? I mean, I didn't find these sequence of small steps. So here's where something really interesting comes up. And that is something that we saw last time, which is P implies Q is the same as, it's identical to, it's contrapositive. What's the contrapositive? Start from not Q. And try to get to not P. If you can find a path from not Q to not P, then you'd have proved not Q implies not P. Remember we showed last time not Q implies not P is exactly the same statement as P implies Q. Right? It's exactly the same statement. It means exactly the same thing. So if you're proving this, you may as well prove that. Right? So this and this achieve exactly the same thing. Okay, so this would be a proof by taking the contrapositive, by contrapositive or contraposition. So let's see what happens if you try to prove it in this direction. So now the contrapositive says if D is not odd, right, then N is not odd. D is even implies N is even. Let's see if we can do that. Well, D is even. So D equal to 2 times A. N is even. So N equal to 2 times B. Okay. Well, D is even. We know that D divides N. So implies N equal to D times E for some E. Implies N equal to, what's D? It's 2A, so it's 2 times A times E. Implies N equal to 2B, where B equal to A times E. Easy, right? So something strange happened here, right? Oh yeah, sorry. I'm sorry? Oh, yeah. So you're right. So you can, okay, so since this is an and, okay, you can really pull it apart. Okay, you can carry it along with you if you want. It'll just get carried along here, and it doesn't bother anything. You can see that if I add in this and this, if I say this and D divides N, this and D divides N, it just carries along, right? It doesn't do anything. It doesn't change. We know it divides. I'm sorry? Okay, so what I'm claiming is we know that if we know both of these are true, this is definitely true, and this is true. And I'm saying this implies this, right? So if this implies this, then this and this implies this and this. So what I'm claiming is that here's another rule. I'm saying if P implies Q, then P and R implies Q and R, always. Okay? And vice versa. Sorry, it's these two. It's always going to be different. Yeah, yeah. I'm sorry? E is some number, right? D divides n, right? If D divides n implies there exists E such that n equal to D times E. Definition of divides. Right? Yes?
How do you know that D divides n if you're assuming conformity? If you start with not Q.
Oh, I see, I see. I see. You're right. So let me do it this way. Let me if this, then, sorry, you're right. Okay, so then P implies Q. Okay? Okay, so now we are saying if for all, okay, so let me rewrite the statement for all D and N such that, okay? Okay, so I'm just using it to define my universe. Belongs to Z plus such that D divides N, okay? If N is odd, then D is odd. Okay, so now this is our universe. This is what we are living inside. Right? These are the numbers we are living inside. I'm sorry, yeah, this is, I'm glad you asked. This is much clearer. So this is the universe that we are living inside. These are the only numbers we are considering for it. Right? It's an infinitely large universe. It's all those D and N where D divides N. For those, we are saying whenever N is odd, D is odd. Okay? So now, sorry. Okay. So now we really took the contrapositive, D is even, N is even. And it just became much simpler. Okay. All right, so what I'd like you to think about here is, it's a very simple statement. When you try to go forward, it's very hard to even know where to get started. But then there's this hidden structure, right? Because of this contraposition structure. And even though you can't find a path this way, you can find a path this way. Okay? Now, this is very significant because it helps us understand that there's this hidden structure that helps us draw inferences. You know, we always infer things about the world. You know, we have many, many facts and we infer things about it. How do we do that? Right? So some of this study came about in trying to understand the laws of thought. And as you can imagine, this is intimately tied to artificial intelligence. Right? So as you try to understand inference in artificial intelligence, understanding these rules is extremely important. Okay? All right. So this is a very important proof technique. This is something that you should really try to understand and master because, as you can see, it's, in something this simple, you get completely stuck and then you turn around and it's easy. Okay? Okay, so proof by contradiction. Actually, before we go to proof by contradiction, let me see if there are any questions. Yeah. I'm sorry? Yeah. No, the universe doesn't change, right? Yeah. So if you're saying for all x, P of x implies Q of x, this is the same thing as saying for all x, not Q of x implies not P of x. Why is that? Well, because we are saying this piece in brackets here is the same as this piece in brackets. Right? This is the same proposition as that. Right? So you think of this as, if you call this R of x, then we're saying this is also R of x. This is the same thing as R of x. So this is saying for all x R of x, and that's saying for all x Rx. So there's no difference between the two. They are stating exactly the same thing.
difference between, okay, so you just, because you just corrected how proof that for all DNN such that
Yeah.
device n, and so it's n dot and j dot. So would there be a difference if it was instead proved that for all DNN, if the device n is on, then d is on?
Maybe we'll take this offline. It's too. I'll take it offline. Yes. Okay. Yes. Any other questions? Okay. Let's see. Before we move on, let me just make a couple of announcements about the class, and then we'll get back to the next style of proof here. So, first of all, I'm sure most of you know by now, but in case there's somebody who doesn't, the place to be at in this course is Piazza, right? Because you'll find a lot of information there. There'll be a lot of discussion. You know, this is where you should go, and it'll make your life much easier. You'll learn better. Do it. The other thing you should know about is the course web page. inst.ecs.berkeley, etc. Right? You'll find a lot of important material there. Right? So your homeworks, your notes, etc. As I said before, the notes are going to be posted well ahead of time. They'll only be final by the time guaranteed to be final by the time the lecture comes around, because we are really revising the notes quite substantially. So trying to make them easier, interesting, etc. But if you read the notes well in advance, like weeks in advance, it'll probably be. There'll be a lot of overlap with what we'll actually cover, but it may not be that good. As you get closer and closer, the overlap will increase, but you'll only know for sure when it's there, But of course, a few days in advance, it'll already be there. Okay, a week in advance. So, yeah.
Are you going to expand the class for people?
Yeah, I'm getting to that. Okay, so here's the exact thing on that. It's taking us a bit of time to work this out, but here's the current thing. So some of you, we've processed some of the wait list already, but there's a substantial amount yet to go. At the moment, the plan is to let in roughly about 80 to 100 students, and this will happen by tomorrow. Okay? Now, by tomorrow, most of you on the waiting list will know what the situation is. If you are having, maybe we are taking too long over it and we are being too careful about it, but if there are borderline cases, we might still be agonizing over a few of them. But we'll let the rest of you know by tomorrow, and we might get the borderline correct by then. Now, at that point, most likely nothing else happens. There's a small chance that we might find additional resources and expand it by a little bit more, maybe 20, 30 more by Monday. We'll let you know if that happens. And then if that doesn't happen, if it happens, it does. If it doesn't, it doesn't. And then we are done with the expansion of the class. Some of you have expressed interest in, at that point, sticking on in case other people drop. You're welcome to do that. I have no idea what the chances are of eventually getting into the class. I can only wish you luck if you do that. If you do decide to do that, we'll set up some place where you can let us know that you are actually doing that, so that as spots open up, we can quickly process that list and add you into the class. Okay, so once the dust settles within these next 3-4 days, and we are done with this process, I'll set up a process where you can let us know that you are still in that mode where you're hoping to get into the class, so you're on the short list, and that's what we'll process to let people in as spots become available. Okay, is that all right? Any other questions? Oh, let me see. Let me bring up one more thing. Some people had asked, what about these extra credit problems? So here's the way you should think about extra credit. Okay, exactly how extra credit will be used is going to be, it's a little nebulous, but here's how you should think about it. If you're trying just to, if your purpose is just to do reasonably well in the class and with a certain amount of effort, extra credit may not be the way to do it. Okay? If you are interested in the extra credit, by all means do it, because it's going to be very fun. You know, these are fun problems. These are interesting problems. They'll stretch your mind in very interesting ways. The one way in which extra credit will be used is towards the top of the class, definitely, to decide, you know, what's the border between A and A+. You know, that does require that you do try to go beyond the limits a little bit. Okay? But in terms of, you know, if it's purely a consideration of grades, then don't bother with extra credit. But by all means, otherwise, I would encourage you to look at them. You know, sometimes they might be difficult. Sometimes they'll just tickle your fancy. You know, they'll be. You look at this question that looks impossible, and then you look at it in a certain way, and it just falls apart. And it's, you know, it'll be these will be sometimes very beautiful problems. So again, I'm not trying to discourage you from looking at them. I'm actually trying to encourage you, but I'm trying to discourage you from looking at them for the wrong reasons. Okay? Yes.
Is that because extra credit points will affect the curve, so that it'll actually drag you down not to do the extra credit problem?
No, I'm saying it will not. It's out. You know, if you don't care about, let's say you don't care about getting an A+, and you don't care about extra credit problems, don't touch them. Don't look at them. Okay. More questions? Okay. Okay, so let's go on to another proof technique, which is proof by contradiction. Now, here we are going to, yes?
Are extra credit points harder than exam questions?
You know, harder is in the eye of the beholder. Some people absolutely dislike calculations and anything complicated. And those people might find the extra credit problems much simpler than exam questions. Because, you know, they involve sort of thinking and you know, how you change your picture of the world in interesting ways. And some people find that very, very easy and pleasurable. So you ask those people and they'll say, actually, these are the easiest questions on the homework. I can't even concentrate on the rest. You know, I can't even bring myself to focus. So it depends upon you. You know, it's your mental makeup. And in fact, it might allow you to figure out what your talents are or your inclination. Yeah? Yes? I'm sorry? For the first proof I showed you, can you? For all numbers, for all integers, yeah? Is that what you're asking? Yeah. Yes, it's for all ABC, yes. Yeah. I don't know. Sorry. Okay, so any other questions? I think in your example, whatever, you know, one of the conditions didn't hold. Yeah, good. Okay, so let's move on. Proof by contradiction. So let's prove a theorem that's a very old theorem. It was proved by Euclid, the great ancient Greek mathematician from about 300 BC. So, by the way, is this the first time I'm saying theorem? And does everyone know what a theorem is? You know, these are the things these are the major statements you prove in mathematics. You know, you're proving something, it's of significance, you call it a theorem, right? This is something that somebody proved. It's Euclid's theorem saying that there are infinitely many primes. Remember what a prime is? So it's an integer. It's a natural number, let's say. P is greater than 1 and has no divisors except 1 in itself. Right? It's prime if it's divisible only by itself and 1. So 2, 3, 5, etc. Okay. So there are infinitely many primes. Now, how would you prove it? Well, it seems difficult to do because it seems like in order to prove this statement, you would have to demonstrate infinitely many primes. Okay, you can demonstrate finitely many primes. You can demonstrate lots of primes, 2, 3, 5, etc. And people have worked on these things and they've come up with millions and zillions of primes. But that doesn't show you there are infinitely many. So how do you get to infinity? And the way to do this is to do it by contradiction. So let's assume that there are only finitely many primes. So let's assume that this is false. Assume there are not infinitely many primes. So there are only finite number of primes. Let's even assume what they are. Let's call them P1, P2, so on, up to P sub k. So they are a finite number. Let's call that finite number k. 50 billion and 4,000. Okay, that's the number of primes there are. We made up some number. So, okay, assume that's whatever number it is, that's the number of primes. And now what we are going to do is we are going to do a sequence of implications. So we will say, this implies this implies that, and so on. And then we get a contradiction. Okay. So then we get a contradiction meaning somewhere along the way we have proved Q, and somewhere along the way we have proved not Q. And we proved both Q and not Q. Okay. Well, one of these is true, one of these is false. So we are saying this implies false. Okay, so let's take this proposition. Let me call it R. What we've shown is that not R implies false. So R must be true. Right? So if you okay, sorry. So let's do it in many different ways. So let's leave this aside for now. We said if we assume that R is not true, if we assume that there are finitely many primes, then we are saying then false is true. Right? Because we started with a true statement, assume it's true. We do a bunch of implications, and then we are saying this must be true as well. But it's not true, it's false. Right? So something must be wrong. What could be wrong? Well, our implications are correct. Nothing went wrong here. There's only one thing we did which could be wrong, which is our assumption must be wrong. So R must be, not R must be false. We started with a false assumption. So the only other possibility is it must be true. So what gives us a right to do a proof by contradiction? It's the law of the excluded middle. Remember, when we started talking about propositions, we said a proposition is either true or false. And that seemed like a big restriction at that time because, it reduces your expressivity about the world so much because, the world is full of things where things are ambiguous. Right? Most great thoughts are ambiguous. And so what this says is, here we are not going to talk about any of that. All great poetry is excluded, much of science, many things are excluded. But now, whatever we can talk about, we have great power here because of this law of the excluded middle. Because as soon as we know something is not false, it has to be true. There's no other two ways about it. Right? That's the only thing it has got to be. That's where we derive the power from. Okay, so the other way to see it, if you really want to see it, what we said was, well, not R implies false. Take the contrapositive. True implies R is true. True, of course. So is R true? Yes. If this is true, then it implies R is true. Right? Look up the rules of implication. So that see it any way you want, but formally or intuitively, but you're just trying to get to a contradiction. Okay, now how do we organize proofs? So it turns out, in order to prove this theorem, we'll need a lemma. Every number greater than 1 is either prime or has a prime divisor. Okay? So you take any number greater than 1, .35 is either prime. If it's not prime, it must have some prime that divides it. Okay, in this case, it's not a prime, but it has a prime that divides it. Simple, right? It's obvious, isn't it obvious? Well, we don't know. I mean, we've got to prove it. Okay, okay. So it's something that we can prove, but it's not. It's sort of it's something that we'll put off on the side. Okay? It's a useful fact. It's going to come in useful many times. And so lemma is a useful fact that you use over and over again. You have to prove it. And so you want to prove it once, name it, and don't reprove it every time you need it. Okay? If you were writing a program, this would be like a useful subroutine you have. Okay, so this is our useful subroutine, which, in fact, for this lecture, we are going to believe, and then we'll prove it next week when we have a new proof technique called induction. Okay? All right, so now what we want to do is fill in these steps to getting the contradiction. Okay, so there are only finitely many primes. So let's try to create another one. Let's try to see what happens now if we have only these primes. So let's try to look at the number q, which is p1 times p2 times pk plus 1. Right, in notation, this is product I equal to 1 to k of p sub I plus 1. So let's see how the lemma applies to it. It's a number greater than 1. It's got to either be a prime or have a prime divisor. Okay, so there are different ways of getting the contradiction. okay, so let me do it one particular way. Let's see if it has a prime. So it must have a prime divisor, but these are the only prime divisors there could be, right? Okay, so either it's prime or it has a prime divisor. Okay, so let's say it has a prime divisor. Okay, so if Q has prime divisor, then there exists I such that Pi divides Q. What else do we know about Pi? Well, it divides Q, but it also divides Q minus 1. But also Pi divides Q minus 1. Right? Why does it divide Q minus 1? Well, just look at it. It divides Q minus 1. Right there. Written out as a product of the PIs. It's in there as a product. So it divides it. Now what can you say about it? Pi divides Q and Pi divides Q minus 1. What must be the case? Pi divides Q and Pi divides Q minus 1. Oh look, Pi divides Q minus 1. Oh, so which implies Pi divides Q minus 1. Pi divides 1. That doesn't work, right? That's not true. That's a contradiction. Right? Yeah. Any one of them. Any one of them. You're saying, well, if Q, there are two, if Q has a prime divisor, then it cannot be Pi. So, right? If you assume Pi was a divisor, then we are getting a contradiction. It can't be true. What's the only other possibility? It must be prime. But that's also not true. That can't be true because these were the only primes. So we have a contradiction. Okay? Let me say it a different way. I'll just say it in different ways until you find one that you like. So we started with a finite list of primes. We said these are the only primes. Then we said, let's create this number Q. And let's try to understand what it is. By that lemma, we know it's either a prime or it has a prime divisor. Now we could say, say it slightly differently. I'd say, well, look, it's obviously not a prime because it's not on the list. It's bigger than these numbers, right? So it's not a prime. Q not prime. Right? Because not on the list. It's bigger than the numbers on the list. Therefore, from the lemma, we know that it was either prime or it has a prime divisor. So it must have a prime divisor. Right? So it has a prime divisor. So there must be some one of these numbers on the list which divides Q. But then we also notice that that number divides Q minus 1. And so that implies it divides 1, which is a contradiction. Okay? So our assumption, this whole chain of reasoning started with assuming that the theorem was false, and it led us, in the end, to a contradiction. Right? Therefore, we can conclude that our assumption was false, and therefore, we've established the fact that there are infinitely many primes. Okay? Yes?
Could you explain this one more time, how you initially created Q as Q equals the product of prime?
Yeah, so the question was, could I explain how I created Q? And let me ask you a question. What do you mean by how? Do you mean, how did I define it? Well, the definition is this. It's just a product of the 3i's plus 1. But maybe you're asking, what inspired this choice? Why did this choice come about? Okay, that's a very good question. And you see, and it gets to this question of, well, there's a proof where you actually prove something, but then, the proof is the syntax. This is where you're actually saying, I'm checking step by step that it actually holds. I'm going to prove to you. This is really going to show this to you. But then there's a creative process behind this, which is how do you come up with the proof in the first place? And that's its own story, and that's the thing that I hope you'll learn something about in this course, because that's a most interesting topic, and that's a most useful skill for you to learn. Okay, so often, even though this is the language in which you express a proof, the language in which you think of a proof might be much more pictorial. You might be drawing pictures, or you might have images, or you might be looking at this thing from different viewpoints. And I'll talk about this as we go along in the class. But let's look at this one. Okay, so behind the scenes, we have this number line. Here's 0, here's P1, here's 1, 2, 3, etc. There's P1. And then there are interesting other places, right? Here's 2 times P1, here's 3 times P1, and so on, right? And so if you want the multiples of P1, they are P1 apart. That's how far apart they are. That's why they are multiples, right? But then you look at Q, another number Q, and you ask, well, where's that? Here's P2, and here's 2 times P2, and here's 3 times P2, and so on. And then somewhere around here, you would get the number P1 times P2. Right? That's the multiple of both of them. And now, what you know is, in the neighborhood of P1 and this P1 times P2, you won't get another multiple of P1 or P2. Right? That's the basic thing about numbers, how they work. Right? This is the basic picture about numbers. You have multiples, and they are that far apart. Okay? But also there's this common multiple. Eventually you have two numbers, you can multiply them, you get a common multiple. And now both of them are far apart from that. You have one point where you don't have multiples of any one of them. Right? And so that's what we're doing. We're sort of saying, look, these are, these few primes, finitely many, are supposed to be able to create for you every number. Every number is supposed to be a product of these primes. But as you multiply them together, once you get to something which is a product of all of them, in that neighborhood you won't see anything, any other multiple of them, of any of them, right? So, and we just picked the next one because that's the closest one. And we said, there's no multiple here. How could there be? Right? That's what you think about behind the scenes. Right? That's your image. But then what you're doing in the proof, you don't want this image, because this image is, there's so much that goes into it. Now you take this image and you contract it down and you say, what's the essence of this image? What's the minimum thing I have to say to explain the idea behind this? And these are the only things that matter in that, right? So in order to verify the proof, all you need is this. In order to understand the proof, you'd look at that image. Does it make sense? Yes. Yeah. Oh, pi divides 1. P is a prime. P must be greater than 1. Yeah? Yes. No, it's a proof by contradiction. It's a proof by contradiction.
But would you're saying that Q breaks that contradiction?
Yeah, I won't get into that. It's up to you, right? So, but it's just a proof by contradiction. Yeah. Okay. Yeah. Other questions? Okay, let's do another proof type. Oh my goodness. Okay. Here's another proof by contradiction, which you've probably seen before. It's a beautiful proof, which actually, for the ancient Greeks, it was, I guess, Pythagoras was very troubled by this, because remember with the Pythagoras theorem, if you have a triangle like this, 1, 1, then the length of this is square root of 2. And for the ancient Greeks, a number meant a rational number. The rational number is q. A rational number q is of the form a over b, where a and b are integers, and b is not equal to 0. Right? 1 over 2, 3 over 5, 2 over 4. But of course, 1 over 2 equal to 3 over 4 equal to 2 over 4 equal to 3 over 6. And this is in its lowest terms. You can always cancel out common factors, and you can always get down to something like this, right? You can always make sure there are no common factors between numerator and denominator. So these were supposed to be numbers. You had ratios of, what were numbers? Numbers were like 1, 2, 3, and ratios of these numbers. But then there was a scandal. The scandal was they discovered that theorem, square root 2 is irrational. Okay? You cannot express it as a over b for any integers a and b. There's no way to write square root 2 as a over b. Now, why would this be such a scandal? Why would this be such, it was treated with incredible secrecy. It was like a state secret. Because, you see, it seemed to undermine the whole number system. Because they understood numbers as being, counting. They understood counting because, it's obvious. There's 1, 2, 3, etc. You see it around you. And then ratios, they knew how to deal with it. It's clear. It's intuitively obvious. You can divide one by the other. You do it geometrically because that's what they were doing. But then this seemed to suggest that there was something they didn't understand, and maybe there was something wrong with this whole number system. This perfection they thought they had. There was something wrong with it, and maybe the whole structure would collapse, and maybe, everything they designed using numbers, maybe it would fail at some point. What might happen? So this was a really big deal until it was understood finally much later what was going on with these irrational numbers. But okay, so how does the proof go? Assume for contradiction. That square root 2 equal to a over b. Okay. So now, and assume a and b have no common factors. All right. You can always reduce, if they're common factors, you keep canceling them until you get down to smallest a and b. So now multiply, and and cross multiply, so square root 2 a equal to b. Square both sides. 2 times a equal to b, which implies, 2a squared equal to b squared, which implies b squared is even. Now, if b squared is even, oh, is it 2b? Oh, sorry. Square root 2b equal to a. Square root 2b squared equal to a squared. So which means that a squared is even. Okay. I claim that this implies also that a is even. If a squared is even, a has got to be even. A is a number, it's a natural number. The only way a squared can be even is a is even. How would you show this? Yeah, good. So I claim that we already showed it up there. So so up there, point in that direction. If you let oh, is that what we showed or no? If d is even. No, sorry. It was the opposite direction. So sorry, we didn't show it up there. Okay, so I claim that. Let me just leave this as a lemma. You see how useful lemmas are? Okay. So this is a lemma you will prove for yourself by. Actually, if you try doing it.
I don't even think you have to prove it. Just plug it in. Like it said.
No, I think it's the wrong direction. Let's leave it for now. We are running short on time, but it may be. I thought it was true. I thought we had proved it there. I don't think it is true, but please check. Okay, but most probably we have not. Or if we have not, then call it a lemma and try to prove it. Okay, and think about what proof technique. You'll try to prove it. It won't be easy, and then you'll use one of these proof techniques, and it'll be completely obvious. Okay, all right. So let's just finish up. Okay, a squared is even. A is even. So a equal to 2c. We substitute. A equal to 2c. Square root 2b equal to 2c. Implies b equal to square root 2c. Implies b squared equal to 2c squared. So b squared is even. Implies b is even. So now a is even, b is even. They don't have any common factors. Contradiction. Right? So we first showed a was even, then we substituted, we showed b is even, but then we started assuming with the assumption that a and b had no common factors. So how could it be? The only way is, that's a contradiction, right? We've contradicted something. We have three facts which just don't, this and this just don't hang together. It's a contradiction. Okay. Very quickly, let me do one last proof, which is by cases. There exist irrational numbers x and y such that x to the y is rational. Okay? So we want to show that, so we say that a number is irrational if it is not rational. We want to show that there exist two irrational numbers such that when you raise one to the other power, you get a rational number. How do we do it? It's very hard to come up with such a number, okay? But what we're going to do is we are going to prove that there exists such a number without showing you which one it is. at the end of the proof, we have no idea which number it is. Well, we have some idea, but we can't name one. But the proof will show clearly that there is such a number. Okay? So start with, so case 1, let x equal to square root 2, y equal to square root 2. Okay, so proof. Sorry, let me just, okay. So either, so, okay. Let me just, what should I call it? Let's just do this. Consider x equal to square root 2, y equal to square root 2. So case 1, either square root 2 to the square root 2 is rational. Consider square root 2 raised to power of square root 2. Either it's rational, in which case we are done. X equal to y equal to square root 2 is the answer. Right? Because we just showed square root 2 is irrational. If square root 2 to the square root 2 is rational, then we are done. Okay, but who's going to compute this? I mean, we have no idea whether it's rational or not. So what should we do? Well, let's let x equal to square root 2 to the square root 2. And let y equal to square root 2. Okay, so x raised to the power of y is square root 2 to the square root 2, whole raised to the power of square root 2, which is square root 2 to the power of square root 2 times square root 2. Which is square root 2 squared, which we can calculate. It's 2. So that's rational. This is definitely rational. Okay? So if x is irrational, then let x equal to that and y equal to that. Here you have two irrational numbers, square root 2 to the square root 2 and square root 2. And x to the y is rational. Okay, so we proved the statement that there are two irrational numbers such that one raised to the power of the other is a rational number without really knowing what the answer is. Okay? Again, this is a proof. What are we doing? What's the picture behind it? Well, the picture behind it is, you see, we looked at these three numbers. There was square root 2, which we know is irrational. Right? Then there's square root 2 to the square root 2. So we know this is irrational. And then we looked at square root 2 to the square root 2 to the square root 2. And we said, this is rational. Right? And what we're saying is, you can go from here to here by raising by square root 2 or here to here. We don't know what this is. But whatever it is, you're going from irrational to rational. So either you go in this step or in this step. Right? Okay. See you next time. Oh, sorry. Before you leave, excuse me. Sorry. Just to make sure everybody knows, there's a homework party tomorrow from 2 to 5. Oops, sorry. There's a homework party tomorrow from 2 to 5 in the Wozniak Lounge. Okay.